Oh, hey everyone, this is Amy here. So I've just activated the live cast. We'll wait probably a couple minutes just for everything to smooth itself out, and then we'll begin today's live lesson. All right, so I'm going to kick off today's lesson on curve sketching. So let's get started. Hold on, it's not right. Here we go. All right, so welcome to our first live stream. As mentioned before, this is going to be on curve sketching. So the format is more or less going to be quite simple, 1 hour presentation on the topic, which I'll walk through all the basics and some of the more advanced questions in this area. We'll also have a half an hour Q&A session. Now, I know with regards to maths, it's a little bit hard to sort of just type your questions. So I've got two options for you. One, if you're watching this from YouTube, so YouTube live stream should have a chat box next to the live stream. So if you have a look and check it out on the right, it should be there. You can definitely type your messages there. I have a team here who will be reviewing all your responses, any questions, and we can answer them at the end. Now, another option is you can join our Facebook group. So let me just go over to the Facebook group and show you. Okay, so this is the Facebook group. If you have Facebook, you just type in Pinnacle Live Discussion Group. We'll approve your entry into the group and you can post questions here. So what a lot of students do with me is they like taking photographs of their questions, which works very well for math. So that's something you can do if you have the Facebook app on your phone. Just take a photo, post it on the group, and then we can check it out and answer it at the end. Otherwise, you can simply just go to the chat box that is, let me find the stream. So you can also go to our website. Our website is here. All the materials can be found in that first link as well. So let me just click through. So if you would like and have a chance to download, you can download the student book and follow along today's live cast. It's got all the basically questions in there. And at the end, if you want some additional practice on this topic, you can also download the practice set. All right. That's more or less it in terms of some admin and what to expect. We'll learn as we go. This is our first live stream, so please do be patient. We do try to improve every week. If you have any feedback at all, be sure to post to our Facebook group. So let's kick things off. So a little bit about me. My name is Amy. I'm the co-founder of Pinnacle Coaching College. I basically head mathematics within Pinnacle. Pinnacle was pretty much founded on mathematics and providing tutoring services in mathematics. I myself have over a decade of teaching experience. At the moment, I mainly specialize in Extension 2 and Extension 1 mathematics. So that's kind of where I have a lot of experience in, and I hope to share that experience with a broader audience through this live stream channel. All right, so let's kick things off. So to start, we will have a look at what is a derivative and how it relates to the gradient. So we'll look at both the first and second derivative and how that relates to graphing geometrically. So a couple of basic definitions first. If you remember, a derivative gives us, so f dash x tells us the gradient of a function. Now, by gradient, I mean, you're pretty much looking at the gradient of the tangent to any point. So for example, if I have that as my function, the derivative tells me if I want to look at a specific point. That totally did not look straight. Hold on. Right, so that tells me the gradient of a particular tangent. All right, so with that in mind, we should have an understanding around what it means to be increasing, decreasing, and stationary. Let's start with stationary first. So I think the parabola is the easiest way to understand. At the turning point, if I draw a tangent to it, it would be flat. Okay, so f dash a is equals to 0, so that's stationary. Decreasing means we are sloping downwards. So for example, if you look at, I guess, this parabola, that left side there would be sloping downwards. So that's what is considered decreasing and is associated with the first derivative being negative. And then finally, increasing. Increasing means sloping upwards. So sloping upwards is like if you look at this parabola, that right side, you see that it's sloping upwards. That's what increasing means, and that's associated with first derivative being positive. All right, so that's it in terms of what the first derivative is and how it relates to the gradient of the function and sort of what to look for in terms of features. Let's take a look at what the second derivative is. So the second derivative, you can see that the key point is concavity. What does it mean to be? What does it mean by concavity? So think happy face and sad face. So that's how I usually tell my students. Concave up means think happy face. Concave down, not so happy or sad face. So it's talking about the curvature. So if you look at the concavity of the happy face, you see how it's sort of bending in a particular way. So that is what concave up means. And what you're looking for is the second derivative being positive. Now, if you don't know what a second derivative is, it literally means just differentiating it twice. So let me give you an example. If we have y is equals to x to the power 4, for example, okay, the first derivative, so standard differentiation rule, bring down the power, subtract the power by 1. So that's pretty simple. That tells you the gradient of the function. Then you do this again. So you literally take the first derivative, differentiate again. So bring the power down, subtract the power by 1. So 12x squared. So that's what I mean by second derivative, and that can tell us the concavity. If it's positive, it's concave up. If it's negative, it have a sad face, concave down. And finally, if it's equal to 0, there might be a potential inflection point. Now notice I said potential inflection point because it's not a guaranteed inflection point. So that will require a bit of further testing. So further testing required. So we'll also take a look at the testing required today. We'll be doing heaps of examples today where it's very typical of exam questions in terms of what to expect, how it's structured, and hopefully through these examples, it will help you with your studies as well. Now, just to remind you, there is a chat box on the side. If you do have any questions, feel free to post there as well. All right, moving on. So in these first few examples, what we're going to look at is just that tie between the first derivative and the gradient and how that can be used to map the gradient function. All right, so in this example, we want to identify the values of which x is the graph increasing, decreasing, stationary. So we'll start by analyzing that first. What I normally do is you look at the graph and you see the turning points. So there are two turning points. Those are stationary points. Okay, so what that means is the gradient is 0 or f dash x is 0. So I'll come back to that. Anything that's sloping upward like this part. Yeah, so I'll just put little pluses to remind myself that's increasing. That's also increasing. That's decreasing. All right, so once you've done the map, that pretty much answers that first part. So I'll just note it down. So part A, so it's increasing from this part. So x is less than -2, or this part, x is greater than 3. It's decreasing in that in-between space, yeah, where I draw the little negatives. So x is in between -2 to 3. And then finally, you've got stationary at those points. So stationary at x is equal to -2 or 3. So I'm going to skip over concavity. I'll do that together with the third part. So what we're going to do is use that to sketch the first derivative graph. So I like to draw that underneath. So that's y dash. So you can visualize what they mean. So at -2 and at 3, f dash x is 0, meaning you've got an intercept at those points. Positive just simply mean above the x-axis, okay? And then negative means below the x-axis. So let me just draw this first. So above, so above the x-axis. So you can see that this is above the x-axis, and then in between is below the x-axis, and then above again. Now, roughly, I would say the inflection, it's at 1. Yeah, so that's usually roughly where your turning point should be on the first derivative graph. All right, so how do I know it also kind of looks like a parabola? So for those who are familiar with polynomials, this one is a cubic shape. So cubics are power 3. So let me give you an example, x3 plus 2x squared plus x, for example. Okay, what happens when you differentiate something that's power 3? Well, it reduces down to a power 2 function, which is a quadratic, and that's essentially what you see. So you can use that as a cross-check. All right, so second part, in terms of the concavity, how would that work? So concavity, I think the easiest way to look at that is, let's say that's my inflection point. You can see that on the left of that inflection point, it's concave down. Yes, like a sad face. Whereas on the right of that is concave up. So if I was to answer part B, I will say concave up when x is less than -1, and concave down when x is greater than 1. All right, so with that in mind, we can also use that to draw the second derivative graph, which is basically the derivative graph of the first derivative. Now that just sounds confusing. All right, let's do this. So we can see, I just noticed there's a small mistake here, not -1. I was meant to say 1. That's the 1. Okay. All right, so at 1, that should be a 0 because the second derivative should be 0 at an inflection point. And then concave down, so negative, second derivative is negative. So let me draw that first. Negative, and then on the right side, the second derivative is positive because it's concave up. So you can see I kind of drew a straight line because if you differentiate a quadratic, you'll get a straight line on the second derivative. So that's roughly how I guess the shape, and 1 is the inflection point, so that's when the second derivative goes to 0. Now this live broadcast will be uploaded onto our YouTube channel as well at the end, so don't worry too much if you're missing something or not able to copy down everything, or you feel like you're not absorbing everything. You have a chance to go back and review it in detail at the end of this. It will be uploaded. All right, so moving on. So this next one we'll take a look at is just straight drawing the gradient function. So to be able to draw the gradient function, you go for the same analysis. So you start with where it's stationary. So you can say stationary here, and then stationary here. And then this is sloping downward, so negative sloping. This is positive sloping. This is positive sloping. All right, so based on that, let's draw this. Okay, so we'll start with the stationary points. Stationary points is f dash x is 0, f dash x is 0. Okay, and then negative means below the axis, positive is above, and then positive is above. So let's see how that would work. So negative, so let's have it coming up to B, and then positive, positive. That's not a great looking graph, but I think you get the point. So you can see here to the left of B where it was negative, it's below the axis, and then wherever it's positive, it should remain above the axis. And I know it has to be a turning point here because f dash x is 0, so it has to come down to that point and then continue up. So that's more or less it. I mean, if we know the inflection, let's say the inflection is around 0, that turning point should be roughly at 0. But my graph is not great, but yeah, we don't have more accurate information anyways. Let's move on to the next one. HSC question actually in this area, so we can see how that it's all tied together. All right, so in this HSC question, we can see this one's an advanced graph. It's got an asymptote on it. All right, so let's try to answer the various different parts together, and then we'll use that as a basis for drawing the derivative graph as well. So it goes, for what values of x is the derivative negative? So I think the best way to go about this is to analyze it like we did with the other questions. You go and look at where is it stationary, where is it positive sloping, where is it negative sloping. So coming to this part, so you can see that this is stationary, positive sloping, negative sloping, positive sloping. Okay, so to answer the question, where is a negative? Well, wherever my negative signs are, which is in between -1 and 3. So the answer to that first one is between -1 and 3. Not including -1 and 3 because that's stationary. Second part, what happens to f dash x for large values of x? So if you can grab a ruler or something, right? Or I'll just manually draw this. Let's pick a different color. So let's start with this point. If I draw, hold on. Okay, so if I draw a tangent, you can see that as I approach infinity, the tangents, you can see that it's started off quite steep and then it's getting lower and lower and lower. It's almost stationary. So what that means is the gradient is actually approaching 0. So as x is approaching infinity, you have f dash x approaching 0. Yeah, because you can see that the gradient is actually getting flatter and flatter. I'll suggest just grab a ruler and just have a look. That's probably the easiest way to understand it. All right, so combining these two bits of information, let's try to sketch the first derivative graph. So I have here the same thing. So let me just annotate that again. So stationary, positive, negative, positive. So let's draw this. All right, so we'll start with the stationary point, -1 and 3. All right, so positive means above and negative means below. Remember that. So above, below, coming back up to 3, and then above again. Now, most people get stuck about here because does it go that way or does it go that way? And this is where that part B information, so this part here, becomes useful. What that is talking about is as x approaches infinity, f dash x is going to 0. So let me note that down. As x is approaching infinity, f dash x is approaching 0. So your function should be approaching 0, in other words. So let me just draw this. Let me just make it a tad better. Okay, that's a bit better. All right, so it's going towards 0. All right, in terms of the turning points, as I mentioned, it should be roughly where the inflections are. So based on the graph, it looks like inflections around 1, and there's another one at 5. Okay, so roughly at 5. And that's it. That's the derivative graph. With some practice, you'll get very good at it. So I suggest you can download that resource I was telling you about, the practice set that's on our website. So you can practice that at home as well. All right, so getting to the juicy parts of this topic. How do you actually sketch the curve using calculus? So this summary here, which is also in the student book that you can download from our website, pretty much summarizes the steps. Now, most exam questions will detail the steps, so they will go find the stationary points, determine the nature, find the inflection points, sketch the graph showing intercepts or whatever. Okay, so they will guide you step by step, but it's good to know what are the steps required to get to the sketch. So the first step is to find the first derivative and solve it to 0 so we can identify the stationary points. Then we can study the nature of the stationary points. You actually have two options here. You've got a first derivative table and a second derivative test. I will suggest if we are doing this test for graphing, always do the first derivative table because it gives you the shape of the graph. But if you're very comfortable with graphing, you don't have any issues visualizing the graph, the second method is just as good. It actually saves you a ton in terms of testing values. Inflection points, you look at the second derivative, solve it to 0 first, and pretty much it's just table of values, so second derivative table. And then finally, in terms of the sketching, the main thing is obviously drawing all the points that you identify from the previous study. And I would say the key thing also is to sketch the y-intercept. Generally, there's no real requirement to sketch the x-intercepts unless the question specifies you should identify the x-intercepts. Sometimes it might not be factorizable, so as in you can't actually factorize the expression, so you can't find the x-intercept. All right, so after discussing the theory, I think it's best to see it in practice so you know what all this is talking about. Let's go straight into it. All right, so first step is to look at the first derivative and solve it to 0. So in this case, we've got fx is equal to x to the power 4 minus 4x cubed. First derivative, bring the power down, subtract the power by 1. Same with the next one. All right, so once you've got the first derivative, we then need to solve it to 0. So to solve this to 0, I suggest factorizing it. Okay, so we've identified 0 and 3. And for this first question, we're going to go with option 1, as that's sort of what I recommend if you're doing this for curve sketching. So let's build a table. Okay. So I suggest drawing one continuous table. It just helps you visualize the graph a little bit better. And what you want to do is sort of pick numbers around these points. Okay, so for example, something less than 0, -1, it's a good candidate for testing. And something between 0 to 3, you can pick 1, 2, 2.5, 2.25, 0.5, anywhere really. Okay, so I'll just pick easy numbers, 1, and then something above 3, 4. Okay, so once you've got all of that, it's just about chucking it into the calculator. So obviously you can't see me putting it into the calculator, but what you want to do is find out, for example, what f dash -1 is by substituting it into here. So 4 minus 1 cubed minus 12 minus 1 square. So you get -16. All right, so you get the gist of it. So that's the number you put in. And then you sub 1 into the first derivative, you should get 8. And you sub 4 into the derivative should get you 64. Now, the focus is less about the number itself, it's more about the sign. Because what negative means, it means it's decreasing, so sloping down, then stationary, then sloping down again, then stationary, and then sloping up. And you can see that's the shape you're going to shoot for when we start drawing. Moving on to the next step. Second step is to look at the second derivative. So the first derivative, I'll just rewrite it here, was 4x cubed minus 12x squared. Second derivative, you just differentiate it again. All right, so there we go. Once you've got that, we solve it to 0. So you can see 0 and 2. Now 0 is an interesting one. It actually came up on our first derivative test. Yeah, if you come back and look at it, it came up as a stationary inflection point. Okay, so actually I forgot to actually answer the question. Let me answer the question. So therefore we've got a stationary inflection at 0, and the other one is a minimum turning point at 3. Now to work out the y value is very simple. You just find it by putting it into fx. Okay, so if you find what f0 is, it will be 0 cubed minus 4, 0 cubed, so 0 to the power 4, which is 0. Okay, so same with 3. You find out what f3 is by substituting it into the equation. That should get you 27 with a negative, right? Minus 27. All right, so that's going to be helpful for us a little bit later on. Back to my earlier point, we see an inflection here, and it came up on the second derivative test, which is good. So there is some consistency across the tests. All right, so we again have to test it. Just because second derivative 0 is no guaranteed inflection point, you need to study it. And you study it in the same way. So you pick numbers. Let me just use a different color. You pick numbers around those points and test it. So for example, minus 1, 1, 3 are good test points. And where do you sub it in? You sub it into the second derivative. So for example, for minus 1, you sub it into the second derivative. And then evaluate, that should be 36. So that first one is 36. And you sub 1 in there, put that into the calculator, should be minus 12. And you put 3 in there, it should be 36. Now this time, it's not telling us the slope, it's telling us the concavity. So positive means concave up, concave down, concave up. Okay, so that's more or less it. Now we've basically confirmed there are inflection points. So inflection points meaning there is a change in concavity. So you can see a change from concave up to concave down, and then from concave down back to concave up. All right, so let's conclude. So there are inflection points at, so 0, 0, we already knew about that. And the other one that's new for us, 2. So with 2, again, you just sub it back into the original function. So f2. Yeah, you can use the calculator to figure out where that point is. It should be minus 16. So minus 16 is the other point. So these first 2 steps basically identifies all the features we need to be able to do the sketching, which is the next step. Right, so let me summarize for you what we found so far. So on the first derivative, we've got a stationary inflection point at 0, 0. We've got minimum turning point. Actually, that's not good. The minimum turning point at 3 minus 27. And remember, the table gave us gradients that kind of look like this. Keep that in mind when we're that kind of look like this. Okay, so in test, you've got inflection thing as up here. All right, two together. Okay, so it's inflection. All right, so you've got inflection and then minimum turning point. So that follows the shape of the graph. Now we can actually find the x-intercept in this one as well, which we can do. I'll just show you how. What you want to do is solve the function to 0. Okay, that's how you find x-intercepts normally. And this one, because it's quite easy to factorize, so 0 and 4. So you can see 0 is already one of them, 4 is here. And that's more or less it. That's how you draw a graph using calculus. So to summarize, first step, so let's go back, summarize. First step is to look at the first derivative, solve it to 0, find the points, study around those points, look at the gradients, and then deduce what type of points they are. Second step, if you have to find inflection points, look at the second derivative, solve it to 0, test around those points, see if there is a change in concavity. If there is, then they are inflection points. Then finally, it's putting all the information together. So you've got the first derivative points and then the inflection points. Use the first derivative to sketch. So that gives you the shape. Put in the points. And then if permissible, you can find the x-intercepts. In this case, I haven't looked at the y-intercept specifically because it already came up as 0, 0, so I don't need to go and look for it. So let's apply this same logic to the next question, just so that we can see how the same thing can be reapplied and gives you a chance to practice as well. Now, feel free to work ahead. You don't have to work in the same pace as me. Just work ahead and you can use my answer as a cross-check. That's how you can effectively learn a lot of this content as well. All right, so this is the next one we want to sketch. This is actually based on an exam question. What we're going to do is just follow the different subparts and then see how we go. Okay, so the first one, we are going to find where fx is 0, which is basically all the x-intercept points. Let's have a look. So taking this is already factorized. I'm going to factorize that a bit further using the difference of two squares. Okay, so we can see that I've got -3 from the first factor and 3 from the second factor. Now, what they are, because it came from solving f(x) to 0, they are x-intercepts. So, i.e., we've got x-intercepts at -3, 0, and 3, 0. And that's basically it. Moving on. It goes find the coordinates of the turning point of y equals fx and determine their nature. So this is now going to the first derivative test, solving it to 0, do a table of values. So let's go through those steps. Firstly, what I'm going to do to make things simpler to differentiate is to expand it out. Unless you want to do product rule, you can differentiate as is, but I don't want to do product rule. Let's keep things simple. And I'm just going to rearrange it in power order. All right, so what we're going to do is differentiate it now. Okay, once we've got that, what do? We solve it to 0 and factorize. All right, so I'm down to here. So therefore, we can see that x is equals to -3 or 1. Next, put that into a table and test it. All right, so how do we test this? Same thing, pick some numbers that's less than -3. So let's say -4, 0, and 2. And then you substitute that into the first derivative. So I'm just going to fill out these tables based on what comes out on the calculator. So the first one should be 15 minus 9, 15. All right, what these numbers suggest is increasing, stationary, decreasing, stationary, increasing. So that gives you the shape of the graph. Now, important to look at how this question is worded. It's very typical of an exam question wording. It says find the coordinates. So don't just answer with x coordinate. It means both x and y coordinates, okay? And determine the nature, meaning is it a maximum turning point? Is it a minimum turning point? Is it a stationary inflection? You need to answer all of that. A typical question like this is probably worth about 3 marks in the 2-unit exam. So make sure you're giving 3 marks worth of working, okay? So let's answer the question. We've got a maximum turning point at -3. So I'll fill out the y values next. And then we've got a minimum turning point at 1. Okay, so as mentioned before, to find the actual y value, you sub -3 into the original function. So you want to find what f minus 3 is by putting it in. So that should come out as 0 by the looks of it. And then you put in 1 as well. Put that into the calculator. That should come out at -32. Now that would be a complete answer. That gets you all the points. All right, moving on to the next step. So the next step, we are sketching. And we're not really looking at inflection points here. It doesn't ask us for it. And that goes to show the second derivative or finding inflection points, it's not actually crucial to curve sketching. You only need the first derivative to be able to sketch. So let's put the information to use. Let me just draw the axes first. Right, so I'm going to be flicking back and forth so we can see and follow. So we'll start with the points, right? So we've got a -3, 0, maximum turning point. So roughly here, -3, 0, maximum turning point. So what I would do, let me use a different color. What I would do is just mark it, right? To remind yourself, okay, that's going to be a maximum turning point. And then going back here, at 1 minus 32. So let's say about here. 1 minus 32. That's a minimum turning point. So you can see, okay, I have to kind of join them together. That's what you are shooting for. So let's try if I can do this. Right, that's not too bad. So in terms of the intercepts, now right in the first part, let's go back. So the first part, we found the x-intercept. There's one at -3 and there's one at 3. So let's go back to the graph. So one at -3 and the other one at 3. So let's label that. Now there's also a y-intercept here, which we're simply finding out what f0 is. So putting that into the calculator, or you can do it in your head. It's just 9 times 3, so -27. So that point is -27. Clearly, my graph is not to scale, but you get the idea. And that's it. So let's see if we've addressed the question. Hence, sketch the graph of y equals fx. Tick, we've done that. And then show the turning points. Yes, we have. And the point where the graph meets the x-axis. Okay, tick, tick. All right, good. We've scored all the points here then. Finally, for what values of the graph is a concave down? If we're working with concavity, we are looking at the second derivative. So I'll go back to the graph in 1 sec. So let's see how we can extract that from the second derivative. Firstly, concave down means the second derivative needs to be less than 0. That's your objective. All right, so the first derivative, I'm just taking it from the earlier working. It was 3x squared minus, plus 6x minus 9. So if you differentiate that again, so that will be 3 times 2x plus 6, 6x plus 6. So you can see that's the second derivative. Now, given we're looking for where is a concave down, what you want to do is take the second derivative and solve it to less than 0. So 6x plus 6 is less than 0. 6x is minus 6, x is minus 1. And that's it. Okay, that's pretty much the answer. You can do this algebraically. That's not a problem. But in terms of what that means for the graph, just flicking back to the graph, it means that -1 must have been an inflection point. That's what it means. Okay, because you can see that to the left of it, it's concave down. To the right, concave up. So you can see there is a change in concavity at that point. That must have been an inflection point. And the second derivative just identified which portion of it is concave down, which is, as you can see, to the left of -1. So that's all it means geometrically. Hopefully that all makes sense. So moving on to the next question. Now, this next question, what I'm going to do, let me just flick to it. This next question, what I'm going to do is do things a little bit differently, just to show you a bit of variation. Remember, right at the beginning, I've mentioned there are two ways to do the testing on the first derivative. The first method, which I've used for the last two questions, is using the first derivative table, which is good when you're graphing. Yeah, if you're a very visual person, I suggest the first derivative table. I personally still use the first derivative table. It just makes things a lot easier being able to visualize it. But yeah, like I hate putting things into the calculator. It's too annoying. This is an alternative method. I think it's a tad simpler when it comes to putting numbers into the calculator, but it does make things a little bit harder to interpret. But I'll show you the method just so that you're aware it exists, and just know how to use the second derivative to do the testing as well, as we'll be using that next week to do the hard problems on maximization and minimization. All right, so let's take a look. So first, we are going to do the stationary points and determine the nature. So same steps. First, we differentiate. Okay, and then solve it to 0. All right, so it's either equal to 0 or 3. So as I mentioned, I'm using the second derivative to test them. So just differentiating that again to get the second derivative. All right, that's it. Okay, so what do we do here? We sub it straight into the second derivative to test. I'm going to test 3 first because I think that one's more obvious. 0 is a little bit more tricky. So we're going to test x equals 3. So all you need to do here is sub it into the second derivative. And put that into the calculator, which should be 36. And all you're looking for is the sign. So 36 clearly is a positive number. Positive number, remember, second derivative is concavity. It means concave up. Okay, concave up, meaning that must be a minimum turning point. So therefore, you've got a minimum turning point at 3. Okay, again, to work out the value, just quickly do up top here. You sub 3 into the original function. Don't get confused here. All right, so put that into the original function. It should be at minus 27. Let's test the other point. Test 0. Okay. If you put 0 into the second derivative, you actually get 0. That means it's probably an inflection point. Okay, we can confirm it in the next step when we look at the second derivative table as well, but it's pretty much has to be an inflection point. So we've got a stationary inflection at 0, 0. And that's it. So this is just opening up another way to do the testing. You can see there is no table of values here, less messy in that sense, but also less visual. So if you're a visual person, still go with the first derivative table. All right, so we've addressed the first question already. We found the points, determined the nature. So the next part is to look at inflection points. Inflection points. So start with the second derivative, which I've already got from before, which is 12x squared minus 24x. So the first step is to solve that to 0. Factorize. So x is equal to 0 or 2. Then we have to test this using a table. So 0, we kind of knew it was going to be inflection anyways, but we'll see. All right, so numbers I would probably test is -1, 1, and 3. All right, very quickly, just putting that into the calculator. All right, so the first one is 36. Second one is -12. And the last one, the 3, is 36. So that tells us concavity. So positive means concave up, negative means concave down, positive means concave up. All right, so that means we've got inflection points. Two point, which we kind of knew about already, and a new one at 2. Okay, so again, to find what 2 is, just evaluate what F2 is. Oops. Okay, put that into the calculator. That should be -16. -16. Okay, so normal inflection at 2 -16, stationary inflection at 0, 0. All right, next part. We're going to sketch this stuff. All right, so let me just quickly summarize what we found so far. So we've got a stationary inflection at 0, 0. We've got a minimum turning point at 3 -27. And then we've got a normal inflection, just an inflection at 2 -16. Actually, that's very similar to the other graph we drew earlier, but let's have a look. Now, this time we're running blind a little bit. We don't have a first derivative table, so you'll have to use a bit of experience and guesswork to see what it's going to look like. All right, so 3 -27, let's say it's about here. All right, so that one we know is going to be a minimum, and that one's inflection. So they have to join up. So if you think about it, inflection can only go one of the two ways. It's either like that or like that. Yeah, like that or like that. Obviously, it can't be like that because you can't join it up with that point. So it has to be like this. And then going back up. All right, so that's more or less it. It's a little bit funky here. Let me just clean that up. All right. So once you've got that inflection point, you just go in and point it. It's probably about that, I would say, 2 -16. Yeah, it changes from a concave down to concave up at that point. Now, it says in the graph, show all important features, which we've done, and intercepts. Intercepts kind of implies both x and y intercepts. So let's find the x-intercepts as well. So you can see that x is 0 or 4. All right, so 0 and 4. That's it. That's all the x-intercepts and y-intercepts. All right, so that's all the graphing. Now that we've mastered graphing, let's take this one level up. What if we have another question which involves applying our knowledge of graphing to solve an equation? Okay, so we are trying to solve x to the power 4 minus 4x cubed plus 27 is equals to 0. First, you have to match it up with the actual function itself. So how does that compare to the function? So you can see that bit is the function. Okay, so what I'm going to do is just move the 27 across. So what this statement actually means is you're trying to solve when the function is equal to minus 27. That's actually what you're solving for. So going back to that graph itself, let's use a different color, blue. Okay, you can see that minus 27 is down here. So if I drew a line, y equals to minus 27, that's what you're looking for. You're looking for where is this function at minus 27, which is at that point. And that's your answer. Okay, so going back to answering the question, we can see from the graph by observing the graph, x is equals to 3, because that's when y is equals to minus 27. All right, so just to summarize what we've covered in this exercise, it's going right back. So the first step, we're finding stationary points, determine nature. That stuff we've repeated like 3-4 times now. So you just look at the first derivative, solve it to 0. This time we use second derivative to do the testing by subbing it into the second derivative. If it's positive, it's a minimum. If it's negative, it's a maximum. At 0, it actually came out 0, so it's going to be inflection, so the stationary inflection. Second step, inflection point, solving second derivative to 0. You get 0 and 2. Use the second derivative table to test concavity. Positive is concave up, negative is concave down. Changing concavity suggests inflection points, so you've got 2 at 0, 0. 2 minus 16. Next step, putting all that information together. So stationary inflection at 0, minimum turning point at 3 minus 27, inflection at 2 minus 16, and you just join all of that together. And we've got an intercept at 4 as well. And then finally, we use this graph to solve this equation. So you're solving this to minus 27, meaning you go to the graph and look at where y is minus 27, which is when x is equal to 3. That's your answer. Okay, so that's usually like a 1 marker that distinguishes your band 6 students from your band 5 students being able to utilize the graph and I guess apply a bit of critical thinking to answer the question. All right, so it's actually 6 o'clock right now, but I think we have enough time to quickly run through the next one, because the next one is a very interesting question. It's not your typical curve sketching questions, got nice turning points and things like that. And I think this is the type of questions that's a little bit more advanced. And if you want to push yourself to achieve a band 6 result, you have to be familiar with this type of question and the thinking behind it as well. So let's go through that next one together. All right, so firstly, we're going to take a look at this function. We want to show that fx is, this function fx 3x squared minus 6x plus 7 is always positive. So this part is kind of interesting. How do you show something is always positive? So firstly, this is a parabola. Now, you may have done this when you did quadratic functions, but something is always positive. Like for example, a parabola, if it doesn't touch the x-axis at all, yeah, because this is a concave up parabola being a positive 3 as the leading coefficient. So the terminology for that, what you're trying to do is show that it's positive definite. Yeah, you might have seen this terminology. It just means it's definitely positive. That is it. So how do you show that? You can use the discriminant to show that. So if you look at the discriminant of this function, okay, so remember discriminant is b squared minus 4ac. So b is minus 6, 4ac, and then you evaluate that. So 36 minus that, so that's minus 48. All right, so minus 48, remember what discriminant means? So the fact that it's negative means there are no solutions. Yeah, so it's not going to touch the x-axis at all. And since the leading coefficient is 3, which is also a positive number, therefore we can conclude fx is positive definite. That means fx is always positive for all values of x. That's what it means. Okay, now if you're still a little bit confused, let me actually draw this function for you. If I wanted to draw, so this is just a bit of an extra information. You don't need to include that as you're working, but it just helps you understand what we're working with here. If I was to draw this parabola, right? Just using the very basic stuff, minus b on 2a, minus b on 2a. All I'm doing is working out the vertex. So it's at 1. Put 1 into the function. It's equal to 4. So it's supposed to have a turning point at 1, 4. So if I was to draw this parabola, it's a concave parabola turning point at 1, 4, y-intercept at 7. You can see it does not touch the x-axis at all. That's what we're trying to show here. Okay, that's why it's always positive no matter what x is. It just doesn't go below or even touch the x-axis. All right, so that's a little bit of an extra theory there. How is that relevant? It's relevant in this part. So hence or otherwise, learning a little bit around how to read exam question, hence means you should be relying on the earlier parts to help you. Otherwise means do whatever you want. I always suggest relations in general view and guide you through the process. If you can take the hint from the earlier parts, usually you're on the right path. All right, so we want to show it's increasing. Increasing means show me f dash x is always positive for all x. Justify means explain yourself. All right, don't leave the answer hanging. Don't leave someone to second guess what they're supposed to deduce from your answer. Always address that question. All right, so let's start with showing increasing first. So you need to look at the derivative. So g dash x is equal to 3x squared minus that. So 3x squared minus 6x plus 7. Now, you may have noticed this is exactly the same function as before, which we've already shown is always positive. And that's what you want to use. So since 3x squared minus 6x plus 7 is always positive for all values of x, okay, that's already proven in part A. That means g dash x is always positive for all values of x, meaning it's always increasing. Now, if you're wondering what does it mean to be always increasing, let's discuss this. Always increasing means it doesn't actually have any turning points. So let me give you an example of something that's always increasing. The cubic It's not always increasing, but mostly increasing. Yeah, but that's a good example. It technically has a stationary point there, but always increasing means it just keeps going up and up and up. Yeah, it doesn't have any turning points. It doesn't come back down at any point. And that's going to be relevant when we try to sketch this a little bit later. Yeah, so having that understanding is good. And decreasing is the other way around. So it just keeps going down and down and down. All right, so moving along. Find any points of inflection. So let's take the derivative, which we've got. What was it? It was 3x squared minus 6x plus 7. Differentiate that again. All right, so 6x minus 6. How do we find inflection? You solve that to 0. So x is equals to 1. Don't forget to test. All right, so chuck that into the second derivative and test it. So that's minus 6. And then putting 2 in there, so that would be 6. So negative, positive, concave down, concave up. So we've got an inflection at 1. And then you find out what G1 is. Should be at minus 5. Okay, so now that we've got an inflection point, let's sketch this. Now, if you think about it, we only have 2 pieces of information here. One is the fact that it's always increasing. 2 is we've got an inflection, not a stationary inflection, just an inflection at 1 minus 5. Okay, that's all we've got. So you can see why this stuff is a little bit difficult, because if you think about it, you've got nothing more. Now, I find that especially when it comes to curve sketching, if you don't know what it looks like, plot the points. There is no shame in plotting the points. Yeah, it's about what gets you the marks. So let's do this. Okie dokie. So how do we do this? All we have is a single point, 1 minus 5. Now we actually have another point here. Let me just copy the function here so you know what on earth am I sketching here, right? I don't have any visuals. Okay, so we're trying to sketch this. So we can immediately see that when x is equals to 0, g0 is just minus 10. So you've got another point, which is the y-intercept. So down here, minus 10. Okay, so you know that it's increasing, so it has to go up, hit that point, and then keep going up. That's what increasing means. It shouldn't have any turning points. It shouldn't come back down at any point. If you're struggling, just sub some points. So sub x is a half, sub x is 2, x is 4, whatever. Yeah. So you can just join the points together. All right. So let's draw this. Okay, so that's pretty good. All right. So you can see that we've got an inflection. Actually, I might just try again to make it look a little bit better. Okay, I think that's a bit better. All right, so you can see that point there, it's an inflection point, meaning it's a very subtle point. So it changes from a concave down to a concave up situation. And it's increasing because you don't see it coming back down. It keeps going up and up and up. And on the left, it keeps going down and down and down. All right, so that's what it means to be always increasing. And then there's one single feature, which is an inflection point. And then we don't have enough to be able to find the x-intercept, but we do know the y-intercept is at -10. And that's it. I think that's the more advanced type of problem. Now, if you do have any questions, feel free to stay back and ask any questions in the chat, or you can also go to our Facebook group to post up any questions. So let me just show you guys the Facebook group. So the Facebook group, you can just go into Facebook and type in Pinnacle Live Discussion Group. It should come up. If you don't have any questions today, that's fine. Feel free to join the group anyway, because what can happen is you can make some suggestions on the topic and what you would like me to go through next time. Yeah, I think Facebook is a very useful tool in that sense. You can take a photo and add it into the group or whatever and ask some questions there. All right, so going back to the presentation. So if you have any questions, I'll stay back for another 15 minutes to answer any questions. Otherwise, you can also post them directly into the Facebook group or have some topic suggestions. And as I mentioned right at the beginning, go to our website to download the student material for today's slide deck. Yeah, you didn't have to copy all the questions. It's all there for you. There's also a practice set that's been uploaded, so you can practice all of these concepts and come back to me if you have any questions next week. All right, well, thank you for your time. Hopefully, I'll see you in the Q&A session. That's it for today.